Okay, so this is the last talk of this morning before we go for lunch. And I'm deeply honored to have Andrew Calway with us. I never thought this day would come, the day that I would invite Andrew to come to Mexico. And well, the day came faster than I thought, and I'm really, really pleased to have him here. I think his work is is quite impressive. It has inspired me. It has inspired many people. And there is no doubt that Andrew's work has had a great impact in many, many people, including me. So I'm going to read Andrew's bio, which is also very impressive. Andrew is a reader in computer science, in computer vision, at the University of Bristol in the United Kingdom. He is based in the Department of Computer Science, and he is also a member of the Visual Information Laboratory at Bristol. Also member of the Bristol Robotics Laboratory, one of the biggest laboratories in the UK, if not the largest in the UK. Prior to this, he was a lecturer at the University of Warwick and Cardiff, and a Royal Society visiting researcher in the Computer Vision Laboratory at Linköping University in Sweden. His research covers topics in computer vision and its applications. Computer vision and its applications. He also works, or he is interested in robotics, wearable computing, and augmented reality. And he works regularly with industry and on interdisciplinary projects. In recent years, Andrew Calway has specialized in 3D tracking and scene reconstruction using vision, mainly simultaneous localization and mapping, which is known as SLAM, visual SLAM. That includes relocalization, fast and robust feature matching, and place recognition. He has published over 80 papers in international journals and conferences. And I can tell you that there was a time when the people from Imperial College were competing with Bristol, because at that time Visual SLAM was getting some start, and Andrew's group was very strong and was competing with Imperial. So I'm again really, really honored to have you here, Andrew. So please, thank you. Please add an applause for Andrew. Go ahead.
Okay, thank you very much, Jose, for some kind words, and it's an honor for me to be here, both at this workshop, but also in your beautiful country as well. It's my first time here, and I hope it won't be my last time. So, one thing I was going to say was that I'm really impressed with this type of workshop where there are so many students. I'm a great believer in robotics and computer vision. The ideas, the revolutions come from the younger people. People like me, well, we've done some things and we report at events like this, but the new stuff comes from people like you. So I'm really impressed with this arrangement. I think you should be really proud that you've got students together like this. That's great. So it's my job now to try and tell you a little bit about what I know about Visual SLAM. And I've been doing this now, as Jose implied, for about 14 years. I was thinking about it last night. I think it's about 14 years since I've been doing it. And in that time, the rapid change. So actually, it's quite good, I think, in this, for me anyway, in this talk, to divide it into two parts. One is to try and give you my impression of what Visual SLAM is about and what the challenges are. And as I see the standard techniques that have emerged over the last 10 to 12 years. And we have actually got to a point now where it could be described as a mature technology in computer vision, in the sense that I don't think it's going to be very long before we'll be able to take off-the-shelf implementations of Visual SLAM that are already appearing, but they'll become more and more solid. So what I want to do first in part one is to do that, to give you an introduction to Visual SLAM. And I've pitched it at the level of someone who maybe hasn't seen Visual SLAM before, and I'm going to try and go through it in an intuitive way to give you a feel for what it's about from my impressions of how to do it. And then the second part, I want to document to you about the things that we've done at Bristol. And hopefully that will give some insight into how that technology has emerged, but I still think there's some good ideas in there that maybe can be used in the future. So that's what I want to do second. Okay. Before I do that, I need to thank some people because none of us work in isolation, and I'm particularly keen on working in teams that do interesting stuff. And so I need to thank these people, all of which have collaborated on the work that I'm going to talk about. You'll know some of them. I deliberately chose this picture. This was taken some time ago, so it just shows that people do change over time. I'd also like to point out my good friend, Walterio Meia-Cuvas, the other Mexican in this picture, who some of you may know. And he's a very good friend of mine, and he's collaborated. His input into my work has been especially prominent. Okay, so let's get started with Visual SLAM. As Jose implied, it is visual simultaneous localization and mapping. And what does that mean? Well, to me, it means if I've got a camera, I want to use that camera to determine the position and orientation of the camera. And at the same time, I want to map the surroundings. So that's simultaneous localization and mapping. Why do you want to do that? Well, from a robotics point of view, and I'm being quite wide in terms of robotics, I don't just mean machines that trundle along on wheels or drones. I'm including personal robotics, the whole raft of things. If in terms of robotics, then what it does is it takes away the need for some sort of infrastructure. And that includes positioning infrastructure, such as GPS, but also any pre-built maps. So that's a big thing to try and achieve. And as Richard pointed out yesterday, even if you have GPS, you've got to have systems that can cover when it's been denied or it drops out for some reason. The other thing, though, which I think is perhaps more important, is that it gives the potential for intelligent understanding, because you couple it with computer vision. And as we know, computer vision is making rapid changes at the moment. And if you're using a Visual SLAM system, then you can bring in those techniques, and then you've got a coherent framework for producing the intelligent autonomous system. So in terms of drones, what this workshop is about, it's clear there's huge potential for using it. There's problems at the moment in terms of computational power, as I'll talk about later, but it's going to come eventually. There's no doubt about that. Okay. So what I want to do first is go almost back to basics. What do we actually mean by Visual SLAM? So I'm going to take a toy example first. So here's an environment, quite a strange looking curvy environment. And what I want to do is to have a camera, and I want to localize the camera in that environment while simultaneously building a map. And for this toy example, I'm going to take the case of I'm going to use features to do that. And they're point features, 3D point features in order to do my mapping. So I start, I've got my camera, I take an image. I then detect some points in that frame. And those will correspond to some sort of points in the environment. I've chosen corners here because it's just easy. What I do then is that I move my camera. And I do the same thing again. I detect some points. Now, if I'm lucky, there'll be some points in there that are the same points that was in the previous frame. Now I'm onto something, because I've now done some matching between the camera in one position, camera in another. If I can do that mapping and I do it with enough points, then I can, in simple terms, triangulate where the points are in 3D, the red points here, and I can also estimate the relative pose between the two positions. So my first position of the camera comes as my reference, and now when I've taken those corresponding points, I can triangulate and get the relative pose with where the camera is at the moment. And so that's an update operation. So I've taken another measurement, and I can then say, where's the new pose for my camera? And that's the basic operation of Visual SLAM at a very local level. And then I can keep doing that. I can take more images, and I can keep mapping. Obviously, I need to have enough points here, and there's algorithms that, the number of points you need is well known. The more you have, the better to minimize your noise effects and so on. But I can keep going, and I can keep building maps, and I go points all the way around, extending my map. I go all the way around to complete a circle. Now you notice on here, and I've tried to illustrate in this simple example, as I go round, my estimate of where the camera is gets a bit worse. And also, my estimate of 3D points in the map also gets a bit worse than it was at the beginning. And this is the natural drift that you get when you're trying to do this type of estimation of mapping and position of the camera. You're drifting away, okay, that's coming from the noise. However, there's a way around that, because when we get round to the other end, so just to say we've got our map and localization, but when we get to the other end and we take one more image, if we happen, luckily enough, to see some features that we saw right at the beginning, then we can correct that drift. And this is what's called loop closure. So if you read the SLAM literature, you see loop closure is mentioned a lot. And what it means is that when I reach that point, I can not only estimate the last pose of my camera, but I can correct everything else up. If you like, there's a domino effect. It all but refers back, and I can correct all my observations as long as I've got that loop closure. If I don't get loop closure, and I just keep going, I'm just going to keep drifting. There's nothing I can do about that. Okay? One other thing to say with this loop closure, I can also do it locally. So in this example, I just kept moving away from my initial point. But if I went back again many times, and that's often called loopy motion, if I do it with my hand, then I'll get this loop closure many times, and I can improve locally in my map as I go. So loop closure, very important in order to get a stable, correct map. That's not the end of the story, though, because when I've built this map, if I keep my camera in the map and I keep my SLAM algorithm running, I'm going to be able to track where it is. If I take my camera out and I go home, and I come back again the next day and put it in, what happens then? And that's what we call the relocalization problem. So we've got our map, we put our camera in the scene, we capture some features, and we ask the question, so where am I? And that's the relocalization problem, or the kidnapped robot problem, it's sometimes called. What do I do? Well, in simple terms, what you do is you look around the map and say, well, where could I be? So one way of thinking about it, if I capture some points here, say, does this pattern look like this one, and are these matching points? Or am I over here somewhere, or am I over here somewhere? So you've got almost a search problem. Now, with a huge map and huge numbers of points, this becomes really complicated if you want to do it really fast. And as I'll show you later on, that's one of the things that we've done quite a lot of work on how to do that robustly and quickly. In this case, it was, in fact, my first example, so that's where I am. Okay? So that's the relocalization problem. Let's give you a concrete example of doing all this. This is one of our early SLAM systems, and it illustrates nicely what I've just been talking about. So over here, on the left, you can see our visualization of what's going on in terms of our estimation. This is where we think the camera is. This is the principal axis pointing out. And you can see it building points. I'll say more a bit later about these sort of ellipses that keep appearing. Because this is actually a Kalman filter implementation, and as I'll say later, it's the uncertainty. But you can see it building up the map. These are the feature points that it's detecting. In a minute, you'll see the system get lost, and it will go into relocalization mode. And that's when it's getting to this very difficult part of the environment where it can't see many features, and at that point, it gives up and says, I'm lost. When you come away again, it finds itself. It's relocalized itself in the map. So in this case, it wasn't that the camera's taken out the environment, it just lost track, but it's still needing to relocalize. So that's a basic early visual SLAM system that follows my toy example. Okay, so what's inside these systems? What do you need to think about? What do you need to build? So I've tried to, in this fairly simple diagram, point out the key components. So we've got our images coming in from our video, from our camera. And the first thing we need to do is to take some sort of image measurements. So in the example I was showing, those are our features, our feature points. We detect them. Then you've got two main components. One is the mapping component, and one is the tracking component. So the tracking is estimating that pose of the camera as you're moving around, and the mapping is inserting those 3D points. In doing so, you build a map up here, and you also get your, what I call the pose trajectory, where the camera is. And in some way, you need to optimize this. So this is the point where you say, I want to optimize where my 3D points are on the map, and also the pose of my camera. Stuck onto that, you need some sort of recovery mechanism, if you like, which is the relocalization. And that's going to take the map, and it's going to take some of the tracking, and it's going to try and find out where the current pose is. So that's the basic components. So there are a number of ways of doing this. And I think the differences in the systems we have at the moment are the way they do these type of things. So the first one is, what sort of image measurements are you going to take? And at the moment, there are essentially two main options. One is what I've already mentioned, that's extracting features. The other one is to do what's called image alignment, where you don't take features, you actually take the whole image. And I'll say a bit more about that later. The other thing to worry about is this stuff here. How do you do all this? And what I call this is the SLAM engine. It's the thing that's trundling along all the time, taking all the measurements and producing the map and the pose trajectory. And really, there are two ways of doing that. One is, and it really comes down to whether they're loosely coupled, i.e. the mapping and tracking, or whether they're tightly coupled. Okay? And in a minute, I'll talk about two categories of technique, one of which is a loose coupling, and another one is a tightly coupled one. Okay? But it's how you actually do this optimization that's important. Okay, so let's have a look at image measurements. So as I said, there's two ways of doing it, really. One is to take point features that are sparse in the image, and that gives you a sparse map consisting of these 3D points. Essentially, we take our map points, and these are matched with feature points in the frame. And that then defines the current pose of the camera. The alternative is to try and build a dense 3D map, and in doing that, we make use of a volumetric grid, and then for each pose, we synthesize what the image ought to look like. And then we do dense matching by aligning that synthesized pose with the pose of the current, image of the current from the video. So we align that using pixel differences, and that defines then the pose of the camera. So I'm going to go through these two techniques now. So let's take feature matching is the first case. So in this example, what I've done is, let's assume we have a 3D map, and I've colored the points here to show that they're different characteristics. And in this case, I'm describing feature matching using descriptors. So we have some sort of descriptors here that describe those points when they were first seen. The way it works with feature matching, we have some predicted camera pose. Now that might be, I'm going around mapping, and I was there, or I think I was there. Now I have some sort of motion model that might be constant velocity, might be constant acceleration, and you think, well, given that, I'm going to be here next, I think. And that's the predicted camera pose. From that, you can project the features that you've got in your 3D map into the image plane. And that then gives you, as I've illustrated here, so these points where you think the points in the map should be in this incoming frame. The white circles here are actually important. They represent, if you like, the error in your prediction. So often what we have in our map associated with these points is an indication of how good an estimate those points are in 3D. And so you might think of the mean and the covariance. And from that, you can essentially project that into the image plane and say, well, this red point here, it's going to be roughly here or in this area. And that, if you like, often called gating. It says that I'm going to look in those areas for matching points. And that's what you do. You often detect what we call salient points, points that are interesting, and that gives you some options in each of these search areas. From our 3D map, associated with each point, like the red one here, we've got some sort of descriptor. And we generate descriptors for our yellow points that we've detected in our incoming frame. We then compare those descriptors. So anyone familiar with descriptors, it might be a SIF descriptor, a BRIS descriptor, an ALB descriptor. Up to you. You choose which you think is best. Some of them, essentially the differences here are primarily to do with how quickly you can generate them. You take the difference between your descriptors and then you get a match score. So that's how good, how confident you are that this point here is the match that you're looking for that red one. When you found the best one, then that gives you a selection of points. So you do that for every 3D point that you've projected into your image plane. You find the best match, and so now you've got correspondence between points in your map and points in your incoming frame. What we can do then is try and estimate the pose, and that's what I was talking about in the first toy example. So we've got our detected features here. We know the relationship between here. We know this red one we think corresponds to this 3D point here. This is our point map. So now we're going to update the pose of the camera. And we can do that by an optimization procedure, and we can then get an update of our 3D points and also the pose of our incoming frame. So that's the standard framework, if you like, for feature-based mapping and tracking. What about image alignment, the alternative? Well, that's based on the idea of rather than detecting features, you actually try and align whole images. Now, there's a good reason for possibly doing this. If you're in an environment where there aren't many features, or you've got features that are ambiguous, like edges, then just taking the whole image frame can actually try and avoid those sorts of things. So how does that work? So I've got my incoming frame here. I've got a dense map here. This means I've got a fairly dense volumetric representation in 3D of my scene, and also I've got texture on it somewhere. It's not shown on this image here, but imagine I've also got texture on there, which I've been building over time. I get my new image coming in, and then I try and work out the new pose. And you can simply imagine that by putting your virtual camera here, if you like, and from your model, you can then synthesize what the image would look like if the camera was actually there. So now you've got a predicted image. You then take the difference in some metric space you want to use, and that then you try and find, by looking over this space, which is the best pose. And the best one is the one where it produces a synthesized image, which is as close as possible to the incoming one, as this case here. So that then is your new pose. And this is often called dense matching. Okay? So you've got two options. Either you take features, or you take dense image alignment. Or, in my view, you should do both. But we'll talk about that a bit later. Okay, so what about the SLAM engines? That's the image measurements that we've done. What about the algorithms that are going to turn over and produce the map and the pose trajectory over time? So I mentioned there are, in my view, two different ways of doing this. One is to tightly couple them together, and another one is to loosely couple them. The good example of the tightly coupled version is to use probabilistic filtering. So that might be a Calway filter or a particle filter, two good examples. And I'm going to go through how roughly they work. The alternative is to keep the tracking and mapping separate in some way, and then you really end up with a tracking front end, which is essentially visual odometry. So it's taking in images and basically tracking the pose as you go through. Every so often, you start building a map based on those tracked poses, and you build up your map that way. So I'll just go through these two so we can see the difference between them. Okay, so probabilistic filtering. So the way that works is that we take the pose and the depth map, so this is the 3D map we're building, and we encode that within some sort of state space. And that's going to be the state space of our filter. Then we link that state to the measurements that we're going to take in our image. So the simplest way to think about it is if you're doing feature-based matching, then you project the features into the frame via the perspective projection, and that's your measurement of your state at any given point in time. That's a nonlinear relationship, and so if you want to make this happen over time, you can use, for example, an extended Kalman filter, which linearizes each step. And if everything's nicely Gaussian, as everything is nicely Gaussian, surely, if it is nicely Gaussian, then using something like an extended Kalman filter will give you an optimal estimate of where the pose of the camera and also the 3D position of the points in the map. Nicely, in my view, it also gives you uncertainty measures for those. Uncertainty measures of where the camera is and also uncertainty measures of where the points are. And that comes in the form of a covariance. Let's see that working. So here's another toy example. So we've got some known points here, just to kick the algorithm off. And at the start, we don't know where our camera is particularly. So we've got a high positional covariance, uncertainty. And the center is the mean position where we think the camera is. I'm illustrating it here in 2D, but in fact this would be 6D because we've got the full pose of the camera, i.e. its 3D position, but also its orientation in 3D. We take some measurements of our known points, and then we can update the pose of our camera, and at the same time, the filter will also update the covariance for us, i.e. our certainty about where the camera is. We can keep going. We can also use our uncertainty as search regions in the same way when I was talking about feature matching. We can take some more measurements, update the camera, and so on. We keep going, we keep updating, and at this point, we're away from our known points, so now we want to introduce some new points into our map. When we do that, and this is where on the video I showed you saw those long ellipses, at this point, although we have a fairly good idea of where the camera is, we really don't know the depth of this point. We know it's along this ray, but we don't know the depth. So our uncertainty in depth is huge. Our uncertainty on, if you like, the bearing, the angle of where this point is low. Okay? So think of this as a rugby ball. I know you don't play rugby in Mexico, but it's a long rugby ball. Think about it like that. And then we can keep going. But the nice thing in the filter, Kalman or particle, is that we can update not only the position of our camera and the 3D point, but also update our estimate of the certainty. And in this case, because we're seeing the same point from a different position, we're much more certain about where it is. So we can reduce this. And in the case of an extended Kalman filter, it will just change the covariance matrix for us. And it'll shrink our rugby ball along the long diagonal. And we can then keep going and so on, building up a map as we go. And that's essentially what you saw was happening in that video. These are also all mutually correlated, and that's also inside our covariance matrix. So not only about the uncertainty of a particular point, but it tells us about the correlation between these points. And because these 3 points were all seen together in some way, then they're correlated. We can use, as I said, a Kalman filter, or alternatively a particle filter to do this. The problem with particle filtering, as an aside, in that as the map grows, our state space gets really big, and particle filters do not like being in big parameter spaces. So here's another way of thinking about it. Here's my state over here. So this M is my map, V is my pose of my camera. So I start off in a particular state here. I've got some sort of motion model that tells me where I think my pose is going to be next. And from that, I can produce a prediction. My map is constant, it's not moving. So as an aside, which I should have said at the beginning, one of the things that we always assume when we're doing this is that we're dealing with a rigid scene. People have started to look at is if it's a non-rigid scene. That becomes a lot more complicated. In the examples I'm giving, I'm talking about a rigid scene, so our map stays the same. We then get some measurements, which might be features in our new coming frame, and then we have an update equation where we can take our predicted state and produce our updated state here. And at the same time, we update our covariance matrix through there. And it's in here that we encode all our uncertainties. So far, I've avoided maths. There's loads of maths in all this stuff, but I'm trying to do it pictorially. But because I like the Kalman filter so much, I always show the Kalman filter equations. I personally think everyone should implement a Kalman filter once in their life, at least. It's very therapeutic. I would recommend it highly. So I'm not going to dwell on this too much, just to point out some key things that I've already mentioned. This is our state up here, our state motion model. Up here, this is our measurement models. This is our perspective projection. Here are our predictions. So we're going from one state into the next. And you do that not only on the state and the measurements, but you also do it on the covariance. And then these are all our update equations down here, where we update the state from the prediction through what's called the Kalman gain, based on the difference between our predicted measurement and our actual measurement. And that's the measurement error. And that's our Kalman equations. This is a nice example that shows a lovely toy example similar to my first slide, in that it's just a 1D case. And as the camera's moving along, it's mapping, and there's a lot of drift. The red is the true position of the camera. The red is our estimate. The green is the true position of the camera. And as you see, when it starts to see right at the end points it's seen before, everything corrects itself, and I get the correct pose, and all my rugby balls shrink. Okay? So this is what happens when you do loop closure. You keep seeing within the Kalman filter, you see everything, and so the drift is corrected, and also we correct. If you have a focus on one of these points here, you'll see the map all correcting itself, and all the uncertainties shrink. Okay, so that's doing visual SLAM with a probabilistic filter. And when they first started, so I guess that would be Davidson's original 2003 paper, he used an extended Kalman filter. And we did a lot of our early work on that. And as I'll say in a minute, one of the advantages of it, for small maps, it's pretty computationally efficient. And so you can actually do real-time processing. After that, people thought, well, why do we have to bother with the filter? Why can't we just do this optimization bit? Why can't we just triangulate and get the pose of our camera simply by optimizing something? So that's what happened next. So let's revisit our problem and think about how the tracking and mapping solution would work. Well, what that does is you do an initial capture of features over a small area, and then you've got matching between these features in your frames, and then you can take those and optimize everything, and I'll say a little bit more about how we do that. Essentially what you do is build a cost function and then minimize that cost function, and that gives you a local estimate of the poses and also of the map. Then out of those, you select what are called keyframes. So these are frames that you're going to keep. And you have the relative position of those keyframes. So I've indicated that here by T12. So that's the 6D relative pose of these two keyframes. And associated with those is this small local 3D map. We keep doing that all the way around, doing local operations, and we get relative poses between all of these. So that's, if you like, the initial tracking bit of this loose coupling between tracking and mapping. What you do then is a global optimization of everything. And one popular way of doing that is not try and optimize this map, but optimize the relative pose of these cameras. And regard these pose estimates as our measurements, and then try and optimize where the poses of the keyframes are. And we call that a global optimization. Another way of looking at that is as a graph. So our poses that we've calculated for our keyframes, so our keyframes form the nodes of our graph, and the edges between the nodes represent the relative pose of these two keyframes, which we've got from our local optimization. So we do feature matching, for example, and from that we get the relative pose of our keyframes. And that gives us that relative pose, and then we've got the rest of them, and then we do global optimization over all the keyframes. So you can regard it as optimizing over a graph. And for that reason, it's often known as pose graph optimization. Another slide with some maths, I'm afraid, but I think this is the last one. So how do we do that optimization? Well, one of the popular ways of doing that optimization is use what's called bundle adjustment. And what that's based on is to optimize over the map point. So xj are my 3D points in my map. So if we take the local example, it's probably the easiest way to think about it. We've got our map points are xj, so they're 3D points. And we've got local keyframe poses. So the TIs are the pose of my keyframes, and those are, if you like, the orientation and position of my cameras. So I then build a cost function, C, and I sum it over my keyframes and also over my 3D points. So I'm summing over I and j, over all the keyframes, over all the points. And I build this error metric here. I use this E. I'll just explain what E is first, and then we'll come back to this. The E is simply the measurement error. So xij is the projection of my 3D points. So my jth point in the ith frame, I project it, and that gives me my measurement x, and that's a 2D vector. And then I project, so that's my measurement of that, and then I take my projection, which is this element here. So pi is my projection function, t is the pose of my ith keyframe, and xj is the 3D point. So that's my projection, and that's my 2D measurement. And then I simply find all the poses and all the x's, xj's, which minimize this cost function. So that's my 2D feature measurement. That's my projection function. That's just the perspective projection. That's the pose of my ith keyframe. That's my 3D map point. And so this is my projection. This thing here, rho, that's a robust function to try and get rid of outliers, because outliers muck up the optimization. That thing there is related, similar thing that we had in our Kalman filter. That's my inverse covariance, which allows me to compensate for the uncertainty. So how do I do that? Well, I take my favorite optimization algorithm. Might be Levenberg-Marquette, it's a very popular one. And so basically you try and minimize C by looking over all the TI and all the XJs. Now, as I have explained that, that's computationally quite heavy, because this space is quite big. These things are 6D, these things are 3D. And if you've got a lot of them, that's a lot of things to optimize over. But if you're close to the answer, and locally you are going to be quite close to the answer because you roughly knew where you were before, and you have a guess of where you might be next, so you're quite close to the answer. So something like Levenberg-Marquette would probably work quite well, and it does. The other type of so that was the local optimization. The other type of optimization is this global optimization around the graph of our poses of our keyframes. So in that case, we have a different cost function, still defined in terms of an error function. But in this case, the error function is, if you like, the difference in the poses. So you want to try and find the TIs, all of the TIs that minimize this thing. And so here what you're doing is taking the relative, your measurement of the relative poses, Tij, and you're comparing one with your solution, if you like, the Tjs and the Tis. This error here is defined in terms of the inverse exponential map. I won't go into details of that, but whenever you look at the literature on optimizing pose graph, you'll see that you make use of this 7D error vector, which is actually the inverse of the exponential map. That is all to do with getting a minimal representation of this 6D pose. Okay? And as before, although in this case we're not trying to find the map, we're just optimizing the pose of all the keyframes that minimize C. So that's our relative poses. Tj is the pose of the keyframe J, and T minus 1 is the inverse pose of the ith keyframe. And again, you can solve it using your favorite optimization algorithm, which might be Levenberg-Marquette. Okay, so that's the two ways that you can do your SLAM engine. One is to use filtering, and the other one is to use tracking and mapping. So you might ask the question, so what's the difference? I've implied, as I've been going along, what the difference is, and this is my own view. Nice thing about the filtering, it does give you a rigorous framework that incorporates the uncertainty. The uncertainty, if you like, comes for free with the filter. You get it out of your covariance matrix. If you're doing local mapping and you've got loopy motion that I talked about, so you're continually doing loop closure, this will give you a very good, nice result. However, when you start doing large areas, your state gets bigger and bigger as your map grows. And that means that your Kalman filter equations get pretty big. And that becomes impractical. One of the early solutions to that was to do what we call submapping, which was basically say, well, when it gets to a certain size, I'm going to start again. So you start building a new map, and then you estimate the relative pose of the two, which is a bit like pose graph optimization in a way. But that was the reason why people said, hang on a minute, this isn't scalable, because my filter's getting bigger and bigger, and this is becoming impractical. That's what motivated, really, the use of tracking and mapping. And also, the tracking and mapping does give you higher accuracy. That optimization, regular optimization, combined with the global optimization, does give you higher accuracy in terms of your map and your pose trajectory. It also allows dense mapping. So I mentioned your image measurements can be image alignments, which gives you a dense map. You can't really do that in the Kalman filter because your state then becomes really big very quickly. That doesn't come into an optimization approach. So you can easily build a dense map using the tracking and mapping approach. But drawback is it's computationally demanding. So anyone trying to put visual SLAM on a drone and they want to do dense mapping, they're going to hit a problem about the optimization because it becomes very expensive. So that's the difference between the two. And really, I think what you should choose depends on your application and your platform. If you've got a wheeled robot and you've got plenty of power on it, then you would certainly do the tracking and mapping option. If you're dealing with a very light drone that doesn't have much power, you might, and people are, beginning to go back to this type of approach, because the Kalman filter can be very efficient over a small area. Okay, so that's end of part one. And hopefully now you've got a pretty good understanding of what Visual SLAM is about, how it works, and really the two categories of technique for doing it. Before I go on to part two, just to say, if you want to read up on that, the techniques that are sort of well known in this area would be the original, what's called mono-SLAM, which is the EKF implementation of SLAM. More after that really came PTAM and DTAM, which are both tracking and mapping methods. More recently, you have ORB SLAM, And orb SLAM is a feature-based SLAM system that uses orb as the descriptor, and it uses local optimization and global pose graph optimization. And if you like, the dense analog to that is LSD SLAM, which is actually doing dense mapping, but then local optimization and global optimization. So if you want to follow up on that first part, grab those papers and read through them, and hopefully what you've seen already will be able to get you started. Okay, so part 2 is really to tell you what we've done at Bristol over that period of time of the evolution of the visual SLAM. And my title was actually motivated what our focus was, because what we were trying to do was to make the systems both robust, and by robust I mean if you shake the camera, the system doesn't fall over, and if you take the camera away and bring it back again, the system recovers really quickly, so i.e. the relocalization problem. And also the issue of making things efficient. And we were motivated primarily because we were working with Kalman filter implementations, where if the map grows with a point-based thing, it becomes impractical. So we were asking the question, is it possible to be more efficient in your mapping? Can you come up with a reduced representation? So that's really what these two first things that I want to talk about. The first is, how do you do robust feature mapping, and hence do relocalization? And the second one is, how can I reduce the size of my map, or the size of the state to represent that map, by actually representing the map in terms of planes? The last thing I want to talk about is more recent work, where we got fed up of trying to estimate depth by stereo, and then someone brought out this thing called Connect, and we said, fantastic, we'll use that please, because it gives you depth for free, which is great. And so we've developed a RGB-D SLAM system, and in particular, we've built in very fast relocalization. So I'm going to tell you a bit about that. And if I've got time, I'll say a little bit more about some very recent work which we've done on HDR mapping, where we're trying to build maps with texture which have got a high dynamic range. Okay, so let's start with the first one, the robust feature matching. So this is work I did quite a long time ago now, 2006, with Denis Chekhov and Mark Papilli and Voltario. And really what we were looking at there was, if you're doing dense feature matching, the problem you've got is as the camera moves, the feature, the thing you see, changes. So this is a well-known thing now, that as you move away, you look at it from an angle, what you see is different than what you saw at the beginning. So matching becomes difficult. And one of the things that we looked at was that one of the problems you get is scale. So as you move away or get closer to the feature, it changes a lot. Inside a Kalman filter, though, you actually know what that scale change is, because you think you know where the camera is now from where it was before, so you can use that information to help you do better feature matching. And this is really what this work was about. So let's have a look at that. Essentially what it was doing was, when we detected our salient points, so think back to my earlier slide on how you do feature matching, we take a salient point, and rather than just capturing a small patch around it, we captured multiple patches at different sizes. And the motivation there is that if you're going to move away, or you're going to get closer, then you're going to need one of these other ones rather than the one you captured in the current frame. So we put those into a big database, if you like, and we built descriptors for all of those regions at different sizes around this point. At the time, we happened to use SIFT, but you could use Bristol or Orb, up to you. But you build a database of descriptors at different scales for this point. So that's the initialization once you've first seen the feature. Later on, when you're trying to do matching, what you do then is that you've got an incoming frame. You think you know where you're looking from your prediction of where you think the pose of the camera is, so you get a measurement prediction. You take salient points, you generate descriptors for those patches that you've got for those points, and then we've got to try and find the best match. But the key thing is, in the algorithm, is rather than searching over the whole database, we have an idea of what the scale of this measurement should be, because we know where the camera roughly is relative to where it was when it first saw the features we're trying to match. So you can use that information, if you like, to hash into your database. And you can quickly find out where you should be looking. You do your best match select, which is simply differences on descriptors. That gives you your best location for the feature, and then you can update your filter. And you do that for each of your features in the map. So that worked very well. Here's another example of that system working. So it's matching features, and as it's doing so, it's building this database of representations of the features at different scales. I'll just move this along a bit. Just want to show you the end, because on this system we've got loop closure. So it's gone round and you've got loop closure, and so now you can see that all of the ellipses have all shrunk as it's seeing things again. Beg your pardon? Oh, the colour here, thank you. The green are features that have been successfully matched. The red are we haven't matched them. Okay? So when it all goes red, that's disaster. We've got relocalization there. Okay. We can also do relocalization quickly with that system as well, because if you imagine, we don't know where the camera is. We've got a 3D map. We've got a frame and we've got some features, but we don't know where they are. So we've got this big database which contains descriptors of all our features at different scales. But what you've got to do is, like I said right at the beginning when I saw it, relocalization, you've got a massive matching problem. You've got a huge number of points in your map, and you've just got a small selection that you're trying to match with. The way we addressed that was to use what we call half coefficients. So these are very small Haar coefficients, which are representations in small patches. And from those, you can hash into the database and find out where the best match is for these. And that proves to be very fast, and you can then, once you've got those, you can do the matching, and then you can update your pose. Let's have a look at that working. So this is the same type of system, but it's got that relocalization mechanism. And as you see in a minute, not only can it find out the pose in a normal scenario, it can actually find the pose when the camera turns upside down even. I think we get to a relocalization in a moment. See all the map building up. So there we've deliberately moved the camera to a different position, so it almost instantaneously relocalizes it. Same there. Moved it to a different position. I think on this example we've got an upside down version. Covering the camera up there. We've got relocalization. Yeah, that's the upside down version. So when we covered the camera, we also turned it upside down, opened the camera up, and it instantly found out where we were. So that, if you want to relocalization algorithm, that's a really good one for just vision-based SLAM. Okay, so that's the robust feature matching and the relocalization you get with it. The other thing that we looked at, as I said at the beginning of this part, was how do you cope with the fact that you've got a growing map of these 3D points? And your state is getting bigger and bigger. Well, one thing we said was that particularly when you're working in indoor environments, you're estimating these 3D points, many of which lie on a common structure of some form. And the obvious thing is many of them lie on the same plane, simply because the world around us in the indoor environment consists of lots of planes. So that means that those 3D points are correlated in some way. So you have to ask the question, well, why am I mapping them all individually? Why don't I take account of the fact that they're on the same plane? So that's what we looked at. And what we tried to do was to, if you like, collapse the state. What we want to do is to find points that lie in the same plane, remove them and replace them with a parameterization in terms of a plane. And in doing so, you can reduce the size of the state. So in a simple case, if I've got 1,000 points that all lie in a plane, then I can represent all those simply by the plane equation for that plane. Plus, and this is something you mustn't forget, you also need to know where those points are, which you can either continue to estimate or you can fix them and really reduce the size of the state. But the key thing, if you're going to do this, you must maintain these measurements of uncertainty, because if you don't, things go wrong quickly. And so we looked at how we did that with inside the Kalman filter. There's two versions of this. The first one was this idea of simply collapsing the state. And that's almost the obvious thing to do, is that when the filter is building the map, every so often you look at the points and you say, well, can I find a subset that lie on a plane? If I do, I'm going to remove them and stick a plane in there. So that's what we did. So roughly it works like this. I map points, I keep going, keep mapping, and then at some point I look back and see, well, given what I've got at the moment, can I find a plane? I can in this case. So I replace those 3 points with a plane that I put in my state. And I also remember where those points were on the plane. Now I either fix them, and they become fixed, or I can turn them into 2D points that lie on the plane with uncertainty if I want to keep measuring. So I keep going round, removing points as I go that lie on planes. I can still keep the points that don't lie on planes because I'm going to use those for measurements later, and so on. And then when I go back, I can take measurements still, and that's why I need to know where the points were. So if I want to take measurements, I know this is a plane, and so I can project into it, but I need to know what to project. So I keep going round. I can take measurements. I can include points that don't lie on planes as well, and so on. And then you can keep tracking the pose of the camera. Here's an illustration of collecting. This is the case where, because you can do this also with lines. So if you've got 3D points that all lie on a line, you can replace them with a line. So this is illustrating how the state in my Kalman filter is reducing over from this over to something like this, where I'm replacing all those 3D points with a line representation plus 1D positions of the points along that line. So here's an example of that working for planes. So you can see as we're going along, we're detecting there's a plane, which is the screen here. So a subset of points have been detected as lying on a plane. You insert the plane, and then off you go. And as you do that, you're reducing the state of the filter. That means it can go quicker. So this was very successful in terms of the early techniques of putting in higher level structure into your SLAM. And you could use this for other things. You could start building, and people have built sort of representations of rooms and so on. Okay. So we did that, and that worked well. The only thing with that, though, was that you got delayed introduction of your planes. And also, you had to have this separate mechanism of every so often, in the background, trying to detect subsets of points that lie on a plane. And it was almost a separate operation. And as I said, you also have this delay when you're introducing the planes. So what we looked at then was to say, well, can we do this as we go? Can we detect points and try and grow them into planes almost instantaneously? And then if we can do that, then we don't have to discriminate between a plane detection algorithm and a mapping algorithm. So we want to keep everything together. And so we developed a uniform framework for doing that. This is work actually that Jose did for his PhD with me. And so we actually developed the first way of actually introducing both points and plane into the map in a unified framework. There was no difference. We used the same technique to do both. It works roughly like this. If I've got a reference frame with some points on, then I detect one point. I then get another frame. I detect the same point. And when I introduce it into my map, I don't just introduce it as a single point, I introduce it as a plane with a normal of some kind. Now at the beginning, I've got lots of uncertainty about both the normal and where that point is. But as I go on, I can start to measure more points that might lie on that plane and update things as I go. So in this case, I've said, right, well, I've initialized this point. Because these 2 points here are close in terms of in the initial frame, then maybe they're on the same plane. So I'm going to allow that to grow and assume they're on the same plane. If they are, then my measurements will be consistent. So then I can update the estimate of my plane. And this is as you go along, as the SLAM engine is working. And I can keep doing that and updating, and so on. This point up here, I've recognized as an outlier, that it doesn't lie on the plane, but it still can be in my map, because it's the same process that's working. And then eventually, that will converge to a good representation of that plane in the scene. And this also reduces the size of your state as you go. So let's have a look at that workings. This is unified planar and point mapping. This is a corridor scenario. And what you can see here, at the top you can see the feature points being mapped. The same color corresponds to growing the same plane. And then you can see them being represented in the map at the bottom. You can see them as the global representation here. There's relocalization as well. Nothing's changed in that respect. The nice thing as well is that you can do mapping all on the same plane. So you can actually introduce new points because you know they lie on the plane. So that was the points and unified points and planes. This is another example, but this time it's visual odometry. So we're not doing mapping here. We're just using the plane idea to do visual odometry. And again, you get the same gains because your filter state is reduced. And you get a lot more efficiency in terms of the representation, and so you can go a lot quicker. Take this to the end. This is a long, several kilometers, I think this is. You can see there the map that we've built on top of the projection onto the map. And so it's visual odometry, it's got drift in it, but it's a good, efficient system for doing it using the planes and points. Okay, so the last example we did where we were looking at planes was to say, well, we've got this growing mechanism, but wouldn't it be really nice is if you could, in a single frame, you could actually recognize where there were planes. So this was the idea, is to take an object recognition algorithm that recognizes planes in a scene, and if you can do that, you can initialize the plane instantaneously. So rather than growing it, you can say, right, everything in that part of the image is a plane, and I'm going to assume it is, and I'm going to get an initial estimate on my orientation from my object recognition algorithm. So that's what we did, and that was based on work that I did with Ozzy and Haynes, where we actually developed an algorithm for not only recognizing planes, but also estimating the angle, the orientation of those planes in the scene. So I won't go into detail how that works. You can look up the paper if you want. It's based on a bag of words plus a topic-based approach like document analysis type thing. But from that, we can get not only that this is a plane, but we get an estimate of the orientation of that plane. So now we can use this in our SLAM system, because if I get that frame, I can say, right, well, I'm going to stick that frame in my map, and then I'm going to use that to reduce the size of my map representation. So here's some examples of the type of recognition of planes you get. And here's an example of that working. I think we've got it compared with the thing we saw where we were only using the unified approach. So you can see the planes being recognized here, and that's initializing points in our map. Over here, we're doing the growing technique. So you immediately see the problem you get with the growing technique is you often grow planes but aren't actually physical planes. They're just points that happen to lie roughly in a plane. but in between them, they're not. And that causes problems when you're mapping. But in the case when you're recognizing them, you get much more consistent representations of the planes. You can see the map that it's created there. I think we get loop closure on that one as well. Okay, so we've done robust feature matching. We've done more efficient mapping using higher order structure in terms of planes. The last thing I want to talk about is the more recent work that we've been doing on using RGB-D, if you like the Connect sensor, to do SLAM as well. So we're not the first to do this, because people familiar with Connect Fusion and the other algorithms have taken the output of your Connect, fusing the depth maps together, and you can quickly build up a 3D representation of the scene. What we've looked at is, which is where things like Connect Fusion are less good, is how can you do very fast relocalization in that? So you've built your representation. If you take your camera out, or you shake it a lot, can you find out where you are? So we've done quite a lot of work in that area, which I've done with Tudor Lee. This is our system at the moment. I won't go into all the detail, just point out the important bits. So what you get in is your RGB image and your depth map from your Connect sensor. And from your depth map, you can build up a surface map. What we do then is extract 3D key points. So we extract interesting points in those incoming frames. And based on a map that's being built, that's also got 3D points and also surfaces in it, we do graph-based matching. And this is the key point of the algorithm. So we've got 3D key points, we've got 3D map points. So rather than 2D points that are projected, we've actually got 3D points that are incoming, and we match them using a graph technique, and I'll talk about that in a moment. When you've got the matching, you can do pose estimation, and from that, you take that as an initial start to using iterative closest point, ICP, to align these 3D points with your points in your global map, or your surface points in your global map. So let's have a look at this graph-based matching. So the first thing that we do that's really important is that when we're building our 3D map, we use a volumetric grid, and within each cuboid, if you like, of that, or voxel of that 3D grid, we make sure we only have one feature point, and that's really important. So we keep a sparse representation of the whole scene that's got one feature point, and we only use feature points which we're really confident about. So if we've got a feature point in a voxel already and we find a better one, then we'll replace it. So that's the first part of the matching that's important, and that's a sparse 3D representation of the scene. In terms of the graph matching, the key thing we do there, so the problem is we've got 3D features coming in. So these are our measurements from us. We've selected salient points in RGB. We then have the depth of those points, so now we've got 3D points. We've got a 3D map that we've built up, and the question is, how do I match this to this one? So rather than taking the points individually, what we actually do is take them as pairs. And this is the idea that if I want to match these to somewhere in here, and if I take pairs of points, then the corresponding pairs in here should have similar relationships. The first being, they should be the same distance away from each other. Okay, so rather than trying to match them independently, we say, well, if these two match these two, for instance, the distance between them in 3D should be the same. Okay? So we take pairs, and what we actually do is use a series of measures to get a cost function, one of which is the distance between the pairs, so that's the D measure indicated here. But we also take account of the relative orientation difference between the surface normals, which we can estimate from our Connect measurements and also in our 3D map. And also the angle of those normals to this difference vector. We combine that into a cost function. There's got these 4 elements to it. And then we find the best matching between what's coming in here and somewhere in here based on pairs. And we use a standard graph matching algorithm based on an adjacency matrix to do that. We've got a fast way of implementing that. But the key thing is that you get these pairs that you're comparing rather than treating the points as individuals. So let's see that working. The first bit is standard RGB-D mapping. So in a sense, this is no different from something like Connect Fusion. So you've got, this is Shuda Lee. For some reason, he did this in his bedroom. I'm never quite sure why he wanted to show everyone his bedroom, but he did. So you get to see Shuda's bedroom. In fact, you get to see a 3D reconstruction of Shuda's bedroom with all the detail. So this has been speeded up, by the way. Shuda doesn't normally walk that fast. So you can see all the detail that you're nicely getting. In a minute, I think we see the 3D points that we keep. So these are the points that I mentioned in red. You can just see them. So those are those 3D points that we keep. So that's the mapping bit. But the key bit that we've done is the relocalization. Because when you build a huge map like that, you've got lots of points. The relocalization is really tough. So as this bit of the video shows, if we get it right, then our predicted depth should look like our measured depth. And you'll see that working in a minute. So here's Shuda. He covers it up. And the key place to look is these two here. If he uncovers it, then these look exactly the same. So what we think we're looking at is actually what we're looking at. Then you can see the position of the estimates coming up here. And it's a shame, actually someone asked me earlier if he bought a demo, and I would have done, but this runs on quite a big gaming laptop, and I really didn't want to bring that with me. But if I had, I could show you that this is almost instantaneous. You can cover that up, take it up, and it's, I have a policy actually, and Jose backed me this up, that when I go into the lab when a student wants to show me something, the first thing I want to do is break it. And I did break some of Jose's work, he knows that. I have yet to break Shuda's work, and it's really annoying me, because I want to break this and I can't. So that's, if you're interested in doing a system that's got good relocalization, then I would highly recommend this. Okay. So I won't show, we can do it for large areas as well. So this, if you want to see this video, see me afterwards, but we can do sub-mapping effectively and build this over large areas. But I did want to show you the most recent thing we've done, which is to actually try and build high definition texture maps. So what we're trying to do here is build our map, capture the images, the great RGB images, and texture the models. But to do it by taking account of, in this case, the Connect. It's got auto exposure on the RGB camera. So as you go into dark areas, it changes the gain. But you can exploit that and capture the different gains, if you like, and then combine them together to make high definition models. And so this is work that we presented at 3DV this year. And if I skip near the end, you'll see the quality of the models that we can build. So this is that. But what it's showing here is on the left is simply doing RGB fusion. On the right, this is the HDR. So what you get is a full representation over the dynamic range of the scene. So this is early work, but this is quite encouraging because you're getting to produce quite really detailed models of the scene based on a fairly cheap camera. And that, I think, is where I will finish it. So we can take some questions. And just to say, if you want to ask in Spanish, that's fine, but I'll ask my friend to translate first.